Launched by MIT to really try to address the climate challenge across the entire institute. And I'm here on behalf of our team, my co-lead Raffaella Ferrari, and a set of faculty and researchers from really across the entire institute. So one of the things that I like to start with when I'm thinking about climate, why did I refer to this as a whole of MIT initiative? Well, climate is really a whole of world initiative. And this is a slide from the Intergovernmental Panel on Climate Change, really showing how most of the things that we care about in terms of sectors are connected to climate. A lot of the determinants of health, the environment, food, recreation, climate makes a lot of these things possible. And we care about climate not because of climate per se, but because climate is so intertwined in all of these kind of services that nature provides for our well-being. And to look at that in a slightly more scientific diagram, you have climate change here on the top. This is another diagram from the Intergovernmental Panel on Climate Change, impacting human society, but human society causing climate change through greenhouse gas emissions, but also can adapt to or mitigate that. Climate also affects ecosystems, but ecosystems are intertwined with human society. So all of that creates risks, but also opportunities to think about the broader challenge of sustainability in this very intertwined world. So a lot of the work I do tries to understand the Earth as a system that involves a moving climate and a human system that's affecting that climate. But also trying to understand the interactions of nature-based and human systems in that context. So MIT's general plan, I serve as co-chair of MIT's Climate Nucleus, which is the implementation arm of MIT's cross-institute climate plan. And MIT's climate plan for this decade is called Fast Forward, really trying to respond to the climate challenge on a whole of institute basis and acknowledging that climate touches not only the research that we do, but our educational mission, policy, and affects us as citizens, and we have our own carbon footprint. So one of the core parts of this Fast Forward, MIT's climate action plan for the decade, when we're talking about our research and MIT's function as an innovation engine, is this Grand Challenges program. It was launched last spring, but it had its roots a couple of years ago when different faculty members at MIT were asked to kind of co-create ideas of what kinds of research projects could be solutions-oriented and address a major challenge in the context of the climate problem. So our project, Bringing Computation to the Climate Challenges, is one of the five selected Grand Challenge flagships, and focuses on the idea of climate modeling. And so one of the things that you can think about when you think about a climate model is you can think about the Earth and its the flows of energy and water going around the Earth. The photograph on the left is Earth as seen by a NASA satellite, and the right is a NASA weather model that looks at the progression of clouds. And historically, MIT was very instrumental in developing some of the early weather models. And those kinds of models are widely used. And as you can see from the diagram, very high fidelity and take into account a lot of the data about the weather system to really help us make better predictions. So if you think about the hurricane forecasting, for example, that we've unfortunately seen in the past week, that kind of hurricane forecast is possible now because of the improvements in weather models that have been made over the past several decades. And this decade's weather forecasting model is better than it was just 20 years ago in substantial ways in terms of its accuracy, probability, et cetera. But if you think about these large scale weather models, you can think about how useful that information is in different places and how often you might use the output of a weather model, but not necessarily, encountering a weather model. Climate change is a different type of model. It's basically thinking about the statistical properties of weather on the long term. And there are a lot of climate change models that exist. And again, the Intergovernmental Panel on Climate Change has run a bunch of models to look at forecasts, for example, for global service change relative to 1850 to 1900. A lot of very complicated models, they take a long time to run. But the idea really is that when you interact with a weather model, you often just look at an app on your phone, right? You don't think about running a broader weather model to find out if it's going to rain this afternoon. Unfortunately, we're in the world of a climate model that for those who need climate information, essentially sort of the long-term statistical properties of weather impacts, how people affect the climate, there's not the equivalent of the fast-running information that is provided by an updated weather model. So, I have all sorts of weather apps. It runs the model in the background. It provides all sorts of information ingesting data, and gives me a better sense of whether I need to, how much time I have to go on a bike ride, for example, before it starts raining. That advance is possible because of advances in computation. And there's a lot of potential for those similar kinds of advances in computation to be applied to the climate modeling field. So my colleagues across MIT are trying to bring that kind of advanced computational thinking to climate modeling in two ways. One of which is a project. This is led by my co-PI on the Grand Challenge project, co-led with MIT and partners with Caltech and NASA JPL, called CLIMA, the Climate Modeling Alliance, is to really make a new version, a new, more modern version of a climate model that can kind of run in the background of all of this. Updated code, more modern ability to understand and ingest data, and better predict probabilities. So what we're doing in our Grand Challenge model is really building from this existing effort to think about how to bridge that. And here it's shown in the left here as an Earth digital twin, how to bridge that with communities and users. And even if it's a new fancy climate model, it's still not something that you're going to be able to run on your desktop level on your phone. So what process do we think about to get the information from that model and to get the best real-time information to the communities that need it, and not in a way that's going to require them to have a lot of expertise and a 2-year partnership with the university, which is pretty much the state of the art right now. How do we get that information democratized, flexible, usable by a broad range of different stakeholders? So our approach is to develop emulators of that climate model. And by an emulator, I mean sort of a fast-running version of the model that doesn't predict everything, but predicts what you need. And through advances in AI, to try to develop that emulator approach more flexibly and automatically if possible. So the idea is that you can sort of query the climate model saying, make me an emulator of rainfall, make me an emulator of extreme rainfall over Boston. And you'll be able to do that and provide information on the frequency, for example, of expected extreme rainfall over Boston for 2050, 2080, 2100. And that information could be useful in a wide variety of different ways. One of which is planning. You can think about a variety of different industries who could use this, cities, other kinds of users that are interested in long-term, for example, infrastructure planning or resilience or mitigation, to think about what the impacts on different scenarios are. So this also is connected to all sorts of other kinds of interactions with human well-being. So thinking about the broad space of sustainable development goals, and tries to connect climate as something that really affects humans and can be sort of really connected. And with better climate information, we can see those connections better and better explore that space. So with that, I'll sort of stop there. I'm happy to answer questions about the project, the grand challenges, MIT's Fast Forward Climate Plan. But do want to thank my co-Is, and we're at the very beginning of stages of this project right now, just getting started. So we're looking forward to working on it. It's a 5-year project, and hopefully at the end of the day, we'll have a better emulator and some pilot test cases that we've actually used the new climate model for.